Logarithms in base 10. So today I will introduce this important concept in mathematics, the concept of logarithms. So we will start with the exponential function f, y equals 10 to the power of x. So here it is, and as you can see in the picture, it is represented by this green curve in the graph, which passes through this point with coordinates 0 and 1. So it's the point on the y-axis. So this axis is the y-axis and this was the x-axis. So it passes through this point because 10 to the power of 0 is exactly 1, and also it has to pass through this point with coordinates 1 and 10 because 10 to the power of 1 is just 10. So this is an exponential function, and as an exponential function you see that it's 1 to 1. So there must be an inverse to this function. So let us call this inverse f inverse, and for sure there is a formula for this inverse function. Now, what you may remember is the fact that there is a correspondence between the graph of the inverse and the graph of the original function f, namely that the graph of the inverse has to be symmetrical with the graph of the original function, and this diagonal should be the axis of symmetry. So if you reflect this green curve in the diagonal, you should get the correct curve for the inverse. So this blue curve here is the inverse of the exponential function 10 to the power of x. So this is exactly the thing that we are going to study, and we want to talk about this. So this is the inverse f inverse, while this was the function f. Now, what is interesting about this inverse is that if you reflect this original curve on the diagonal of the first and third quadrant, then any point with coordinates, for example 0 and 1, gets to a point, or is reflected to a point with coordinates which are interchanged. So instead of 0 and 1 we have 1 and 0. Now this point it's projected here to this position, and instead of coordinates 1 and 10 we have coordinates 10 and 1. So this is what we can say about the inverse, that it is constructed from the original function. So if we take the original function y equals 10 to the power of x, we can construct the inverse by interchanging the x and y coordinates. So instead of having y equals 10 to the power of x, we can write that the inverse is defined by the formula x equals 10 to the power of y. And this formula assigns a proper value y to each value of x that we input into the function machine. So f inverse, the inverse function, can be imagined as a function machine, and the input takes the value of x, and at the output we have the value of y. So here I have to say something about this inverse. So what can we say about it? And this is exactly what we can say. I can write it next to it. The inverse is such a function that it assigns to the x the value y such that x equals 10 to the power of y. So let us say that in words. Inverse function, this blue curve, assigns to any value of x such an exponent y that when you raise 10 to the power of y, you should obtain the original value of x. For example, if take x equals 10. So if x equals 10, then we assign the value y to the x in such a way that we ask 10 to what power is 10? Okay? 10 to what power is 10? And we know that it's 10 to the power of 1, so therefore to the value of 10 we assign the value y equals 1, and the reason for that is that 10 to the power of 1 is exactly equal to 10. Okay, so now I will come back to this in a second, but let me now introduce the notation. We have to fill in something here. We have to express the y in some formula, and the way to do it is to introduce the new notation. So how can we write it? The inverse function to the exponential 10 to the power of x is just denoted like that. Y equals logarithm in base 10 of x, and we read it exactly as you heard. Y is the logarithm in base 10 of x. This is the terminology, the new name given to this idea of assigning the proper exponent to the value of x, and the exponent is such an exponent that when the base 10 is raised to that exponent, you get the proper value of x that you input into the function. So instead of this notation, logarithm in base 10 of x, we can use a shorthand notation and simply write logarithm of x, like you can see here. These three horizontal lines mean equivalent. So logarithm in base 10 of x, this notation is equivalent to this one, and this is used very often. And actually, if you do not include the base here as this small number next to the g letter in the logarithm, then it is assumed that the base is just 10. Okay, now here comes the definition of the logarithm in base 10 of x, and you can copy that into your notebooks actually. So the logarithm in base 10 of a positive number x is the power y that 10 must be raised to in order to obtain the number x. Here we have the idea written down in formulae. So the logarithm of this number x is such the value y that when you raise 10 to this power, you get proper x. So this and this both represent the idea, because here in this second formula we have expressed or isolated actually the value of y, and for that we needed the new notation. So y equals logarithm in base 10 of x. Now there is this requirement that x be positive. Why? Why does x have to be positive? Look here. The original function f, the exponential function, had the domain of f was the set of all real numbers, because you could calculate 10 to the power of x for any real value of x, and the range of the function f was just, as you can see, the green function has the range just the positive numbers. So it was the set of all numbers. Well, let me use this shorthand notation. These were r plus, so these are positive real numbers. Now, as you well know, there is this property of inverse function, that the inverse function has the domain and the range interchanged. So what was the domain of the original function is actually the range of the inverse function, and what was the range of the original function is actually the domain of the inverse. So the logarithm has the domain, the numbers that you can input into it, just the real positive numbers. So this is represented in the graph by the fact that the blue curve is defined only for positive values. It's not, it doesn't reach into the third quadrant, as you can see. It's just defined in the fourth and in the first quadrant, like that. So only positive values of x are input into this logarithm function, and you can calculate logarithm only from such numbers. Now let us move on working with logarithms. Let us talk a little bit about this. There is this another thing that we have to talk about. Now, how can we take logarithms, or actually how can we calculate logarithms? So imagine some scenarios, some simple scenarios. The first one, imagine you have a number in the form 10 to the power of n, where n is an integer, and you want to calculate the logarithm of such number. For example, the number would be 1000. Okay, logarithm of 1000. So you may imagine that 1000 is actually 10 to the power of 3. So it's a logarithm of 10 to the power of 3. Now, what is the logarithm of 10 to the power of 3? According to the definition, logarithm of such number should be the power that 10 should be raised to in order to get 10 to the power of 3. So, if you think about that, you see that it must be exactly 3, because this is the power that 10 has to be raised to get 10 to the power of 3. It's so simple. So logarithm of 1000 is just 3. Okay? Imagine you have to calculate the logarithm of let's say 0.01. So it's the logarithm of 10 to the power of -2, because it's 1/100ths. Okay, so it's 1 over 100, it's a fraction. And if you want to calculate such a logarithm, you have to ask yourself the question, what power should 10 be raised to in order to get 10 to the power of -2? Okay, and there is the obvious answer, it is the power of -2. So the logarithm of this number here is -2. And we could go on with similar numbers forever. There are many various choices of n. You can imagine logarithm of 1,000,000, logarithm of 1 over 1,000,000,000, and so on. All of those logarithms would be exactly these numbers n. So we can generalize this and say that the logarithm of 10 to the power of n, where n is an integer, is just n. Okay? Because it's the power that 10 has to be raised to in order to get 10 to the power of n, and that's it. Now, another situation of interest here would be the situation with numbers in the form 10 to the power of r times the nth root of 10 to the power of m. So let us think about what the logarithm of such numbers would be. Okay, logarithm of this. Let us start with simple examples. Some simple case, for example, logarithm of the square root of 10. Okay, this is really a simple one. So you may remember that square root of 10 is actually 10 to the 1/2 power. So it's the logarithm of 10 to the power 1/2 that we are going to calculate. And now you may ask yourself, what power 10 should be raised to in order to get 10 to the power 1/2? And that power that we are talking about is called the logarithm of 10 to the power of 1/2. And you may see that it's really 1/2. It's 0.5. So you see, you can get also the fractional value as the logarithm of a number. Now, let us consider another situation, logarithm of a number 10 times square root of 10. Okay? If you have to calculate such a logarithm, you have first to change this number in the brackets to 10 to some power, and then you can easily calculate the logarithm. So it's the logarithm of 10 to the power of 1, this is just 10, times 10 to the power of 1/2, which represents the square root of 10. And now you can see, using the power laws, that this is the logarithm of 10 to the power of 1 plus 1/2, so it's 1.5. Okay, so it's 10 to the power of 1.5. And you see that the answer to this question, what is the logarithm of 10 to the power of 1.5, is just 1.5. So you can have a number like that as the answer for what the value of the logarithm is. Now, in a general case, as was proposed here, this general case of numbers in this form, so 10 to the power of r times the nth root of 10 to the power of m, you proceed in the same way. So you have the logarithm of, and now it's 10 to the power of r times, and as you well know, the nth root of 10 to the power of m is just 10 to the fraction m over n. And now, having this, you have to multiply two numbers, two powers of 10, so you have to actually add their powers. So it's the logarithm of 10 to the power of r plus m over n. So this would be the power of the base 10. So what is the logarithm of such number? So actually it has to be r plus m over n. So it would be an integer value plus a fraction, and that would be your answer. Now, of course, any number in the form 10 to the power of y, we can take any number in this form and calculate its logarithm. So what would be the logarithm of 10, so we are talking about this part here, of 10 to the power of y, where y is any real number? So the answer is, of course, obvious. The logarithm of such number would be just y. And this real number y would answer the question what the logarithm of 10 to the power of y is. So, well, actually the only trouble here, if we want to calculate logarithms, for example, say you want to calculate the logarithm of 5, well, the trouble is you have to somehow be able to replace 5 by the proper power of 10. So it's the logarithm of 10 to something. To what? We don't know. Well, actually we do. We do. Just look here at these two statements here. Okay, so let us talk about these two obvious consequences. So for any number y, any real number y, you can say for sure that a logarithm of 10 to the power of y is y. So this is exactly what has been said a second ago. So yeah, this is just a copy of this. The y number here can be any number, any real number, so 10 to the power of -5, 10 to the power of +100, and so on. But this second thing here is interesting. Let's talk about this. Imagine imagine that you know that y is the logarithm of x, and moreover you know that 10 to the power of y is x. This is equivalent with this. So the logarithm is the power that the base 10 should be raised to in order to get this value of x. And now if you replace this y in the exponent by what it is, it's the logarithm of x, you get the following: 10 to the power of logarithm of x equals x. Okay? So if you raise 10 to the logarithm of x, you get x. So this answers my original question. Logarithm of 5, well, what is it? It's actually the logarithm of 10 to some power. And what power? Actually the power of logarithm of 5. So simple as you see this is. Now, well, you may say that this is nothing new. It doesn't add anything to what we have learned. Of course, well, it would not help us in our trials to find the exact value of logarithm of 5, but it gives us the correct picture of what this logarithm of 5 is. Logarithm of 5 is the proper exponent that 10 has to be raised to in order to get this number of 5. There is another perspective that we can choose to consider these two equations, and it's the perspective of the function and its inverse. So if we look at this using this perspective, what we can observe is the following. This equation here, it says first calculate 10 to the power of y and then take its logarithm. So actually it amounts to the following: f to the power f inverse of f of y equals y. Okay, so if you take the function f of y and then take its inverse, you end up with the original y. And the second formula here amounts to the following: if you take f of f inverse of x, you end up with the original value of x. So these two requirements were general requirements required of the function and of its inverse. So if you combine the function with its inverse in both possible ways, you should always get the identity or the identical function. So whatever you put in, you get at the output. Okay, now the last thing. Last thing to talk about is how to calculate decimal logarithms of using a calculator. So this is some scientific calculator, and if you want to calculate logarithms, you use this button here, log. So this log, this is the decimal logarithm, so the logarithm in base 10, and if you want to calculate the logarithm of any number, you just type log button, you touch it and click it, and then actually you input the number and type equals sign, and what you get is the answer. It is the value of the logarithm. So you will practice that in what follows in the exercises and in the examples.